Let's make an example using separation of variable method to solve our PDE in transit. Okay, so one example of separation of variable for 1D heat equations. Okay, and again, this is a metal rod. As we talked before, this is a metal rod. The length will be L, so from 0 to L. And we say this L is 50 centimeter. And we have our function fx is equals to x, L minus x. And this is x is a function represent the temperature. So when the x, the space x is belong to 0 to L over 2, that is fx equals to x. Okay, so if x is over L over 0 smaller than L over 2, the temperature distribution is linearly increasing as you increase the space. Then if my x is in between the L over 2 and L, so if x is in between L over 2 smaller than L, then that will be, the temperature will be as function of L minus x, okay? So that is the temperature, okay? The temperature at T equals to 0, so it's the initial temperature, it's the initial conditions. Uxt will be equals to x, fx. So at initial temperature, the temperature distribution along the whole route is given as the initial conditions. So this is the initial condition. Then there are some other boundary conditions for this metal rod heat equations. The boundary condition is U0T is equals to 0, ULT is equals to 0. So at all time, the ends of the rod, the temperature will be equals to 0. Okay, so this is the boundary conditions. Then how we write these heat equations? How we write this 1D heat equation? We already derived this before. It will be UT. So the temperature part will be first derivative of the time part will be the first derivative of temperature is equals to alpha U XX. And this alpha is what? This alpha is actually the heat, the effective thermal conductivity, right? So it's the thermal conductivity divided by the density times the heat capacity. And here I can give you a number, it's 1 centimeter per square second, So this is the heat equations for the 1D dimension for rod heat transfer with some initial condition and boundary conditions. And we are trying to solve what is our U as function. So our solution, we are trying to solve our final solution, which is the temperature as function of space and time. Okay, we want to see this transit from initial to the final, what is in transit temperature distribution. Then we will use the separation of variables. So using separation of variables. Okay, use separation of variables. And as we said, the first step for the separation of variable is trying to separate two functions. One function is as function of time, one function is as function of space. And a product of them will be temperature distribution as function of space and time. So uxt is equals to fx gt. Okay, so this is the separation of variables. And you can see that we want to use this separation of variables to represent our initial ut and our initial uxx. Then how we can use the separation of variable form to represent our ut. This is the first derivative of time. And as the only function as function of time is the gt, so fx gt, and this is the first derivative of time as a dot, right? We use dot to represent the derivative of time. So fgt will be equals to ut. How about uxx? Uxx will be the second derivative of space. So it will be f double prime x gt is equals to uxx. Then we are trying to use the separation of variables to replace the original PDE. Then we have fx gt, first derivative of time, equals to alpha fx double prime gt. Okay. Then you can see that we have the function, the ODE as function of the x. There is ODE as function of the t here. Then we can separate them out. So to put the function of x on one side, to put the function of t on the other side. Then we have f double prime, which is as function of x over f equals to gt over a g, and fx, so that is alpha g here, and that is equals to k. This k is called separation constant. Separation constant, okay. And after we separate out the x part and the t part with its own ODE, then we just solve them individually, the t part, the time part, and the space part. So we got our two equations. One ODE will be g minus alpha g k is equals to 0. Okay. The other part ODE will be a second order ODE, which is f double prime minus kf equals to 0. Okay. So the first ODE is a first order ODE. It's very easy to solve. And you see this, the alpha and k are constants there. So you can imagine the g part should be an exponential function as function of the t, right? So the gt is easy to solve. It's just some constant times e to the alpha k t. And that is the gt part, which is as function of time, and this is an exponential function. But for the f part, is become a little bit complicated. This is a second order ODE, right? The second order ODE, and we don't know the boundary condition yet. If the boundary condition is a homogeneous boundary conditions, we can still solve it. This will become a Sturm-Liouville problem set. Let's see whether it can become a Sturm-Liouville problem set or not. So f double prime minus kf equals to 0. We don't know the boundary condition yet. Let's try to put our number in, trying to figure out what is the boundary conditions for fx. Okay. So we have two boundary conditions previously. We have u0t, ult equals to 0. So let's put the number in. So u0t equals to 0. And that means our gt f0 will be equals to 0, right? Then what is our gt? Gt will be ce to the alpha kt. So it's ce to the alpha kt times f0 equals to 0. Then because this part, the exponential part, won't be 0, that means 0 has to be equals to 0. So this derived f0 has to be equals to 0. Okay, let's see the second conditions. ULT equals to 0. That means the GT FL equals to 0. And GT is same, will be CE to the alpha KT FL equals to 0. And since this part won't be 0, similarly as previous case, then that's derived to the other condition, FL will be equals to 0. So the second order ODE become F double prime minus KF equals to 0 with the boundary conditions is F0 equals to 0, FL equals to 0. So this is a homogeneous ODE with the homogeneous boundary conditions. And if you test the Sturm-Liouville problem set, it's validate. So now we have this, let's assume that this K is minus K lambda squared. So basically will be F double prime plus alpha squared F equals to 0 with F0 equals to 0, FL equals to 0. And if you test all the coefficient inside this second order ODE with homogeneous boundary conditions, it's become a Sturm-Liouville problem. Okay, it's become a Sturm-Liouville problem, and you can assume that we can solve it, and we will go to orthogonal basis site such as sine, cosine functions. Then the final solutions will be an infinite series with this kind of orthogonal basis site, and with the boundary conditions, we can solve the PDEs. Okay, we can solve the PDEs. I'm trying to solve it. I'm trying to solve this Sturm-Liouville problem set first. Okay. So we have F double prime plus lambda squared F equals to 0 with F0 equals to 0, FL equals to 0. Then to solve the Sturm-Liouville problem set, we first need to know what is the eigenfunctions and what is the eigenvalues, right? And since this is a constant ODE, then we assume that F will be equals to e to the Rx. Because this is a constant ODE, so the solution set will be look like an exponential function. Then F double prime will be equals to R squared e to the Rx. Then you put this solution set into the original ODE, what we get is R squared e to the Rx equals to minus lambda squared e to the Rx, right? So you get the R squared equals to minus lambda squared. Then you have the R will be equals to plus minus lambda I. So this is the root of your R. You will get two roots because this is second order homogeneous solutions. You will get two roots. And this root has some imaginary part. Then we can assume that this exponential functions will turn into the sine and the cosine function, right? Since the e to the plus minus ix equals to cosine x plus minus I sine x, then that means our final solution fx will be a linear combination of those cosine and sine function. So it's c1 sine x lambda x plus c2 cosine lambda x. So that is our fx term. And because we have this homogeneous boundary conditions, we know that we can solve what is our C1, what is our C2. Okay, so when our F0 equals to 0, FL equals to 0, we can derive. So F0 equals to 0, that means the x equals to 0, this term will be equals to 0. And this term will be equals to 0 since F0 equals to 0. That means our C2 has to be 0. Then FL equals to 0. Since this term already equals to 0, that means the C1 sine Lx needs to be 0. So that leads to C1 Lx needs to be equals to 0. And since this C1 couldn't be 0 anymore, because if C1 and C2 both equals to 0, that will lead to your final solution Fx to be a 0 solution, and we don't want that. Then the C1 is now 0. That means the sine Lx needs to be 0. Then what kind of sine Lx needs to be 0? Then only when the sine, the Lx equals to n pi, that will be equals to 0. So Lx the L lambda, the L lambda will be equals to n pi. That means our lambda is equals to n pi over L, and it's from the integer 1 to until infinity. Then you have this final solution. Okay, the final solution Fnx will be equals to some basis sites. This is all sine basis sites. Will be equals to sine n pi x over L, where the n starts with 1, 2, 3 until infinity n, all the integers. Okay. And what is our k? The k is equals to minus lambda squared. So will be equals to n squared pi squared over L squared minus sine. Okay, so this is our k. This is our k. Then after we know our Fn, we can also know our Gn. The Gn is some constant times e to the alpha kt. And we already know what is our k. So that is c e to the alpha times n squared pi squared over L squared. There is a minus sign there, t. So that is our Gn. That is our Gn. Then our final solutions will be a product of them, right? And since each of them will be a sum of orthogonal basis sites, then our final product, the uxt, will be equals to what? Will be equals to fx times gt, because it's a product of the two function. And that will be equals to the sum of fnx gnt, because there will be a linear combination of all the infinite series. Then what we have here will be equals to the sum from n cn, okay, cn sine n pi x over L, that is the Fn part. Gn will be e to the minus alpha n squared pi squared over L squared t. So this is the final solutions for our uxt. And this is in transit solutions as function of space and as function of time here. But here, this is now the final solutions because we still don't know what is our coefficient. In order to know our coefficient, we have to use some initial conditions or boundary conditions we haven't used before. We already used what conditions? We already used this F0 equals to 0, FL equals to 0, and that is from the U0T and ULT. The only boundary conditions we haven't used is the initial condition we haven't used. What is the initial condition? Is the temperature distribution at time equals to 0, the initial time, equals to Fx. And this will be equals to when time equals to 0. So this term will become 1. That will be equals to the sum Cn sine n pi x over f. Okay. And you see this is very familiar format. This sign is Euclidean series, right? It's an orthogonal basis site. The Cn is the coefficient for the orthogonal basis sites. This Fx is some continuous function. It's a continuous function to represent the initial temperature of the rod. So in order to get this coefficient, how we solve this coefficient is the inner product basically of your Fx and the orthogonal basis site and normalized by the orthogonal basis site square. So the Cn will be equals to the inner product of Fx sine n pi x over L divided by the normalization part sine n pi x over L sine n pi x over L. Okay, so this is how you get the coefficient part. Okay. Then the next is how we get the coefficient part. Use our already initial known parameters. So we have this Cn equals to the inner product Fx sine n pi x over L divided by sine n pi x over L sine n pi x over L. And we already proved this orthogonal basis set sine n pi x over L sine n pi x over L will be equals to this is equals to L over 2. Then that means when it's divided by L over 2 will be equals to 2 over L, the inner product Fx sine n pi x over L. Okay. Trying to prove if you don't remember how you get the inner product of the sine n pi x over L. Okay. Then the next is we know Fx distribution is equals to x when x is over L smaller than L over 2, equals to L minus x when the x over L over 2 smaller than L. This is a continuous function. This is a continuous function. Then for the each part, for each region, it will be a continuous function. So when we do the interproduct, we will do the interproduct for each region. So the Cn will be equals to 2 over L. The first region we will do the integral is from 0 to L over 2. And the continuous function is x. So x times sine n pi x over L dx. Because the weighting function is equals to 1 in this case. So there is no weighting function here. And you will do another part of the integral, which is 2 over L from L over 2 to L. And that is L minus x. L over minus x times sine n pi x over L dx. And that is how you can get your coefficient part. And how you do this integral. We know that, let's make an example of this one, and you can try to practice for your integral for this one. So for example, the L to L over 2 x times sine n pi x over L. This is the integral between two functions. And the integral over two functions from a to b, u dv, will be equals to u times v, the product of these two functions from a to b, minus v du from a to b. Integral of a to b. A to B. Okay. Let's figure out what is our U and what is our V. So let's assume that U equals to X, then du will be equals to dx. Let's assume since U equals to X, then the other part will be dV, right? This part will be dV. So dV will be equals to sine n pi x over L dx. Then what is the V part? Will be the integral of this part. So it will be negative L over n pi cosine n pi x over L. Okay, you can try to validate. Then we figure out u, v, du, dv. Then we can solve this initial integral. Will be equals to u times v. So minus x L over n pi cosine n pi x over L. Integral is from 0 to L over 2. Okay, and the minus the integral from 0 to L over 2 v du, which is negative L over n pi cosine n pi x over L. Du will be dx. Okay. And then you can try to solve it by yourself. We won't waste of time here. So in the end, this part will be equals to L squared n squared pi squared sine n pi over 2, where n equals to 1, 2, 3 until infinity. And using this method, you can also try to solve what is the second term integral. It's very similar and it's very easy after you derive this part. So in the end, the Cn will be equals to 4L over n squared pi squared sine n pi over 2. And you notice that n has to be integer. And when n is equals to an even number, so when n is even number, then this Cn will be equals to 0, because the sign some integer times pi will be equals to 0. So the Cn will be 0. Then in the end, let's just write with the Cn, with our whole form of the temperature as function of x and t. So finally, our uxt will be equals to the sum, which is Cm, where this m will be just the odd number, because the even number, the coefficient will be equals to 0. So let's just use the odd number. So m equals to 1, 3, 5 until infinity. Cm times sine lambda m x e to the minus alpha lambda m squared t, where the lambda m equals to m pi over L. Cm equals to 4L over m squared pi squared sine m pi over 2. Okay, so this is our final solutions of the PDE. The temperature as function of space and time will be a linear combination of the infinite series, which include the Fourier series part, and also the exponential part, which is as function of the time. And this is only the odd number, because the even number of them will be equals to 0, because the coefficient will be equals to 0. Then we can use the MATLAB or other program you are familiar with to evaluate the solution, how the temperature of the route can be distributed as function of time, as function of space.